Hello, everybody. Welcome back. So we have seen, I have prepared too many materials for these two lectures, so I won't be able to finish all of them. Let's see how far we can go. We've seen the definitions of GPDs and a brief physical picture for the GPDs as the three different regions, 2D lab for quark and anti-quark, and one distribution amplitude. And similarly, we can have the picture for gluon GPDs, but I will not talk about that today. And we have seen that GPDs it contains intriguing physical pictures by giving us a 3D image of the parton inside the proton. That's why we are interested in measuring them. And they can also give us the angular momentum contribution from each flavor of the partons. And now the question is, how do we see the GPDs from experiments, and what signatures do they show when we make any measurements? And that's the phenomenology of GPDs, and that's the subject for this session. And this is actually, it can be thought of in unified pictures, and we can motivate this picture by going back to the large angle 2 to 2 scatterings of meson-meson to meson-meson as shown here. This is a 2 to 2, and it's very simple because the kinematics is exactly constrained by the momentum conservation. By having the final state meson C or D with a large transverse momentum QT, we are sure that there is a hard scale in this blob, and therefore we can confidently apply the perturbative QCD or factorization to understand this kind of processes. And now going from the right to left, we only have an additional diffracted hadron from H prime in the forward direction. And this we call single diffraction. The word single means that only one of the initial state hadron undergoes a diffraction and the others doesn't. And in fact, if the other hadron is also diffracted, we were able to show that that will break the factorization. So you don't have the convolution of two GPDs. You only have one GPD at a time. And this, again, is different from the PDF, because PDF, we can have one PDF in the initial state as we have for DRS. We can also have hadron-hadron collisions where we have convolution of two PDFs. But for GPDs, we only have one at a time. And again, we need a hard scale to make factorization possible. And that hard scale is the same as the hard scale here. It's given by the large momentum QT of the other two particles, C and D, in the final state. And you can then see the difference between the single diffracted process and the large angle 2 to 2 scattering, because the single diffractive process contains two scales, one hard scale given by the QT, and the other soft scale T given by the momentum transfer from P to P prime. And therefore, the minimal kinematics for studying GPDs must be a 2 to 3 process, because to have a GPD, you need a single diffraction from H to H prime. But on the other hand, to apply the QCD to factorize this process into a GPD, you need a hard scale. That requires at least the two particles, C and D, which gives us the large and balancing transverse momentum. And this two-scale feature then motivates a physical picture. And we use this picture to think about this kind of processes. How it happens is it has two stages. The first stage is that this diffraction happens first. It gives out a state, which we can call it A star. This A star has a low virtuality, but it has a large energy. So it moves with the moves almost on shell and happens at a long distance scale. And then it meets the other beam particle B, and participates in this hard interaction to produce the two hard scale C and D in the final state. And this two-stage picture underlies everything I'm going to talk about in the following. And the necessary condition for the GPT factorization is, again, the hard scale must be much greater than the soft scale, which is given by T here. And T can be as low as lambda QCD. And before moving on to talk about how we proceed from the two-scale picture, let me first point out that this 2 to 3 process type is actually very generic. It contains almost all of the processes that are used to probe GPTs. And this 2 to 3 process can be classified by the type of the other beam particle. In reality, we can have an electron beam as given by here. We can have a photon beam. We can have a meson beam. And for electron beam, because if you have an electron scattering by lepton conservation, we know that final state must have another electron. So that's given here. And we only vary the other one, which can be a photon, which can be a meson, and can be a virtual photon that decays into a lepton pair or other things. And this actually gives the processes that have been studied. The first one is the so-called DVCS. I will talk about that in a moment. The second one is called the DVMP, or deeply virtual meson production. And this one called double DVCS, and blah, blah. And then we can have a photon beam. Where can we have a photon beam? Well, a photon beam can be created at the JLab. HAL-D has a photon beam. And you can also think that this photon as a quasi-real photon, as being generated from a forward electron scattering, something we can get from EIC or also JLab. In this case, a photon scattered with a hadron can produce a lepton pair, and it produces a photon pair, a photon meson pair, a meson meson pair, etc. And the first process is called the time-lag Compton scattering, or TCS in short. And the last type is we can have a meson beam such as a charged pion beam. And this can be created at the facilities called Amber in J-Park. Amber is, I believe it's in CERN, and J-Park in Japan. And this pion beam is created as a secondary beam by hitting the proton first at the target and create some hadrons, and then you select and accelerate these pions to have pion beams. And all these processes fit into the 2 to 3 template that we have shown. So the power of introducing the so-called single diffractive process is that we can have a unified picture for all these processes for GPDs. And now I will use the DVCS as an example to introduce some phenomenology of GPDs. And using the picture we have seen, it actually contains a lot of beautiful physics. And the starting point is we first look at the kinematic configurations. We have the proton scattered by this electron, and the proton is going in the forward direction, and the electron is scattered to a final state momentum Q1, and with the balancing photon radiated. And we can call this a photon electroproduction process. And the hard scale here is, again, given by the large transverse momentum of the scattered electron. And using our two-stage picture, this happens by exchanging a virtual state, A star, between the diffracted nucleon with this electron. And the scattering between the A star and the electron creates another electron and the real photon. So in this picture, we highlight the two-scale features. And then the question is, this mysterious state A star, what it is? Well, the reason we are highlighting this A star is because it has a very low virtuality but large momentum. So it behaves like a quasi-real state. And because of that, we can make make an expansion over the particle contents in this A star. And so the simplest one is we have one single particle, which can only be a photon as required by quantum number conservation. And going beyond that, we can have two partons, a QQ bar, a gluon-gluon pair. We can have three partons, QQ bar with another gluon and three gluons. And we can have four partons and more. And now, to connect to the literature, the first photon exchange process is normally referred to as Bethe-Heitler process. And this has nothing to do with GPDs. And the other one are collectively called deeply virtual compton scattering, or DVCS. And I will tell you why we named this in a moment. And the power of using this two-stage picture is that we can treat these two sub-processes in the same way as the expansion of the same state, A star. So they are treated on the same ground. And then about this expansion is in terms of the numbers of particles in the A star. But recall that A star has a low virtuality, but it moves with a large momentum, and then it enters a short distance interactions here. So as A star is propagating, the particles inside A star are characterized by a soft scale T. So they are separated by this kind of scale. But they have to merge in the short distance scale characterized by QT. Having one more particle in this A star will bring us one more suppression given by the ratio of these two scales. And in this way, by this expansion in terms of numbers of particles, we are actually making a power expansion. So having one more particle give us one more power suppression. So we call the first process with the photon exchange a leading power, and the two parton exchange will be next to leading power. Three partons will be next to leading power, and etc. And so that's the beauty of the two-stage picture. We are getting a consistent power counting. Not only we are separating this same process into Bethe-Heitler and DVCS, we also get a consistent power counting. We identify the Bethe-Heitler as the leading power and DVCS as next to leading power. And then for this expansion, we naturally picture them in the frame as displayed here. This frame is chosen at the center of mass frame given by the collision of this A star and the electron. And this, we take this to be along the z direction, with A star moving along z and electron moving along minus z. And this 2-to-2 collision produces an electron and photon. And this happens on a single plane. This is the orange plane shown here. And on top of that, we have this A star coming from the diffraction of this nucleon from momentum p to momentum p prime. And because this is not along the same line, they define another plane called the diffractive plane in this blue plane. And these two planes define an angle that we call azimuthal angle phi. And this phi is the angle that is of particular interest in experiments, and I will tell you why. And we also describe this 2-to-2 scattering by the angle theta. And because we make an expansion over the any possible state A star, and we decompose the whole amplitude of this 2-to-3 process as an expansion over the sub-amplitude of each individual A star. And for each of them, we separate the whole amplitude into two parts. The first part is the diffraction part from N to A star. And this is followed by the hard scattering between the A star and the electron that produces the final state particles. And now we know what phi is. Phi is exactly the azimuthal angle dependence of the hard scattering part. So by rotational property, we know that it's captured by a phase determined by the holistic state of A star and the electron beam, and it's solely given by this phase factor. And in obtaining the cross section from this amplitude, we sum over all possible sub amplitude and take a square to get the cross section. And in doing that, we'll get a sum over all possible interference between different A star states. We have on the left-hand side, we have A star, and on the right-hand side, we have A prime star. And this will interfere. And this interference will generate another phase. And this phase factor is given by the holistic difference of the interfering A states. So it's given by the holistic difference of lambda A and lambda A prime. And because the cross-section is a real quantity, we know that this phase will turn into a cosine of and sine of this phi. So in this way, we know why the azimuthal angle is interesting, because it characterizes different A states. And we also know how the phi distribution is generated is completely determined by the quantum interference of different spin states of the A star. Specifically for the process we are looking at, we can start with the simplest one, the Bethe-Headler process. Here we have a photon exchanged between the nucleon and the electron. And the leading order diagram is shown here. We have two. The photon scatters with the electron, and this can happen from this process or this kind of process, one T channel, one U channel. And now we know that the transition from a diffracted nucleon to a photon is described by the matrix element of this electromagnetic current, and this is described by the form factors F1 and F2. So it's not given by GPT, it's given just by the electromagnetic form factors, the same as what we have in the elastic scattering of electron and proton. And now, because we're interested in the azimuthal angle phi, and we have seen that that is given by the holistic state of the exchanged state, this photon state. So elementary treatment is we insert a complete polarization sum inside here, and that decomposes this amplitude into two parts. One is given by the photon, and the other give photon form factor, the other given by the hard scattering matrix element. And this photon has three holistic states. The first is we have plus minus helicities, and we can have a zero helicity states. The first two are called transverse photon amplitude, and the other one is called longitudinal photon helicity amplitude. So I have told you that this photon channel counts at the leading power as compared to the QQ bar and the gluon channel. But if you perform this power counting more carefully, you see that only the transverse photon amplitude will scale at the leading power, while the longitudinal photon will scale at the next leading power. It contains one more power suppression. So it should be treated in combination with the two-parton channel, which is the DVCS. And for this channel, we have at the leading order a QQ bar exchanged here. And the leading order diagram is given by this diagram and this diagram. So this happens by exchanging a virtual photon between the QQ bar pair and the electron. And this is similar to what we have in DRS. The electron gives out a virtual photon that hits the parton pair, and then the parton pair emits a real photon that we observe. And exactly because of this, we call it DVCS, because this parton process happens as the scattering of a quark with a virtual photon and producing a real photon and a real quark. So this is a deeply virtual Compton scattering, and that's where the name comes from. But here, because we are having this QQ bar pair with a low virtuality but a large momentum. And that's something similar to the DRS. The low virtuality can be neglected when the quarks enter the hard interaction. So we are allowed to make approximations in the place indicated by this dashed line. And this dashed line is the same as the approximation hook that we used in the Wednesday lecture for treating the DRS. And this, in the end, will factorize the whole amplitude into a GPD with the hard scattering coefficient. They are convoluted in the particle momentum fraction x, and x is integrated from -1 to 1. And the difference between this and the DRS is that we have two GPDs that contribute at the same time, the unpolarized GPD and the polarized GPD. The first one is defined with the projector gamma plus, the other one is with gamma plus gamma 5, and they both survive. And they survive because we are treating this at amplitude level. And at amplitude level, there's no place for the spin average of the proton to come in. We have to deal with the most general spin states. And that's why they both contribute. But for both GPDs, the QQ bar pairs have overall 0 helicities. And I'm also putting here the hard coefficient form at the leading order. They take a particular simple form of x and psi, and the dependence on theta and phi are factored out, and I'm not writing them explicitly. What interests us here is the azimuthal dependence, and we have seen the first two channels, a photon channel at the leading power, and the next to leading power contains a longitudinal photon and QQ bar. And the leading power has the helicity plus minus 1, and subleading power has only helicity 0. This is the power counting at amplitude level. And now we look at the cross-section. The cross-section is obtained by first summing over these two and all others amplitude and then take a square. And we keep track of the power contents all along. And then that gives at the leading power the square of the leading power amplitude. Subleading power is given by the interference of leading power and next to leading power amplitudes. And in terms of the phi dependence, we have seen that the interference between two different A star spins will give us this cosine and sine phi modulations. At the leading power, we only have plus and minus 1 helicities from the photon states. So this will give us no phi modulations. Although you may say that the plus and minus 1 can interfere to give us cosine 2 phi, but that interference, if you work carefully, they do not occur at the leading power. They occur only at next to leading power with 2 power suppressions. And then the interesting thing is that next to leading power, when we have the interference between leading power and the next to leading power, because the leading power has plus minus 1 helicities and subleading power only has 0 helicity. So their interference will give us nothing but cosine phi and sine phi modulations. And we can take a closer look at this kind of interference by converting this amplitude square in terms of the cut diagram. On the left of the cut is the amplitude, and on the right is the conjugate amplitude. And the leading power is the interference between the two virtual photons. So this is something called the twist 2, or you may call it the leading power diagram. And the interference between the leading power and next to leading power then is at the next to leading power is given exactly by the interference of a virtual photon and a QQ bar. And this interference generates a cosine phi and sine phi. Why this is interesting is because we are having an interference pattern that we do not see at non-relativistic quantum mechanics. The reason is in non-relativistic quantum mechanics, the particle type does not change. Their quantum number is fixed. So we only have interference, say, between the different helicities of the same electron, but we never have the interference between different numbers of particles and different types of particles. And that's a unique feature of quantum field theory. And that is what GPT makes it possible, because we have a quasi-real state, and that gives us interference between a photon and a QQ bar. And this interference generates cosine and sine phi. And experimentally, we know that even though we do not know the presence of GPT, or we know nothing about the GPT, as long as we can measure this kind of cosine phi and sine phi, we know that underlying this process, there is a GPT contributing. And that gives us the unique signals for GPTs. And now let's put them together in terms of the differential cross-section. And we are only interested in the phi distributions. So on the left-hand side, we have the cross-section differential in terms of t cosine theta and phi. And forget about t cosine theta. We only look at phi. And on the right, separating the phi dependence. We have constant distribution multiplied by 1 plus the cosine phi and the sine phi. And these two coefficients will depend on the GPDs. And this is in terms of this picture. And this is simplified because I'm using an unpolarized proton. If you generalize this calculation by including all possible polarizations of the proton, you get a lot of more distributions for phi. And because the proton can have a transverse polarization, you get another azimuthal angle, which is phi s here for the spin of the proton. And you generate more azimuthal modulations with different coefficients and different spin combinations. And the spins can be controlled in experiments. And that gives us control to measure all these different modulations and their coefficients. And please don't be scared by these details. I will not go into that. I will only flash you through this complicated expressions of these coefficients in terms of GPDs. And they depend on GPDs through this kind of convolutions. That's how GPDs enter these coefficients. And we have, in total, we have 4 of them, and they are all complex valued. But so that give in total 8 real degrees of freedom, and but we have exactly 8 polarization asymmetries, and that allows us to solve that equation to completely invert the GPD convolutions from experiments. And that's the all I want to say about DVCS. So any questions regarding this? I'm going to switch the topic. Yes.
Possible like use like a S channel reaction to as a GBT signals. This here is all about T channel.
In terms of S channel, what do you mean?
So compared to the T channel like process, or like a S channel reaction to have a GBT.
So by T channel, do you mean something like proton transitioning to another proton in the final state?
Like having A star.
A star being a space-like state, you mean? So you want it to be a time-like state? So, but you need to ask, how do you generate a time-like state? The time-like state is something like what we have in E plus E minus. But there you have E plus E minus annihilating into a virtual photon, a time-like virtual photon. But that time-like virtual photon is very virtual. It has a large virtuality. It's not something soft, it's something hard. And here, the reason we are having a T channel, or space like A star is because the P and P prime are almost collinear to each other, one in initial state and one in final state. And if you want to create a time-like state, you need to have something like a PP bar that annihilate into a state. In that case, it's no longer GPD. So you have two proton states, P proton, antiproton in both in initial state, and you will no longer have the GPDs as we defined here. Instead of having P in initial, P prime in final, you have both P and P prime in initial state. That doesn't give you a GPD, that give you something else.
That channel like process not access the GPT information.
Right. But there are some related studies, not to the one you are proposing, but something as we have both P and P prime in the final state. And that gives us something called generalized distribution amplitude. That's something else. Any other questions? Okay. When do we stop? I mean, when is this lecture until? It's depending on how many minutes I have. I still have a lot of stuff. Okay. Okay. So let's move on. We have seen the phenomenology of the GPDs in the place of DVCS. And I have shown you how the different states of A star generates different azimuthal modulations in a very beautiful way. And using all these different azimuthal modulations, we can extract these different GPD convolutions. What do this convolution look like? And so now let's take a closer look at these GPT convolutions. I showed this to you before, but I didn't go into the details. So here in DVCS, we have GPDs such as H and GPD-E convoluted with kernels that depends on X and psi with plus or minus R epsilons. And we have the similar thing for H tilde and E tilde with different, with just the minus sign here. So, for all these convolutions, the X is integrated from -1 to 1 completely. And this whole integrals are commonly referred to as Compton form factors in the literature. And the reason they are called Compton form factor is exactly from the name, deeply virtual Compton scattering. Yes. And the key feature I want to point out is that these convolutions have no dependence on the external scales, either the Q scale, the QT scale, or the polar angle theta that we have seen before. And therefore, they are quite independent from the process we are using to measure them. And the advantage of that is that these convolutions can be treated as the single form factors that enter the experimental measurements. And these are denoted as the calligraphic HE and H tilde. And this is one example of the polarization asymmetries. They enter in this way, and they have an overall coefficient that depends on the polar angle theta. And these Compton form factors are unknown, but we are sure from this expression that the theta dependence is definite. And this is something we can measure from experiments. And even though we know nothing about this square bracket, we know the overall theta dependence. And this is related to the scaling in DRS. And this is the scaling in DVCS. So by confirming the scaling phenomena at least we'll be sure that it is the partons that are dominating the underlying dynamics. So this scaling has been confirmed experimentally at JLab Hall A in this paper in 2006. And on the left panel, you can see that this is measuring a certain Compton form factors, and they are constant as a function of Q squared. And the scaling kicks in already at this scale, 1.4 or 1.6, and kind of surprising, but that's experimentally confirmed. So we are at least confident in some way that we are applying the right factorization formula to describe the DVCS. But on the other hand, that means it's very difficult to extract the GPDs because they only enter through this kind of convolutions and with no other external handles from the Q, QT, or theta. So it's very difficult to extract the X dependence of GPDs. And one way to see that is, even though you constrain the left-hand side of all these convolutions, you can still have a lot of freedom for the GPDs that enter these integrals, because you can define something called a shadow GPD, denoted by this S here. This shadow GPD can survive from all the experiment measurements related to DVCS. And but they give zero integrals to this, and they cannot be distinguished from the real GPDs. And for example, in here, the blue curve is one model of GPD, and the other one with a huge wiggle is another GPD. And they differ by something called shadow GPD. And they fit to the same common form factor on the left-hand side almost exactly. So these two GPDs will not be distinguishable if we only measure DVCS. And why is that? That's something quite different from inclusive processes such as DVCS. And the reason is we are looking at exclusive process. And by exclusive process, everything is at amplitude level. The factorization is at amplitude level. So the X variable, the momentum fraction of the partons, is just like a loop momentum. This is just a virtual loop. And this loop is never open up. So you never actually pin down to some particular value of X. X is always disentangled as the complete integral from -1 to 1. And this is in sharp difference from the DRS, because if we just look at the DRS, immediately we see that DRS is a cut diagram. This represents something like a cross section, and the cut line puts the final state partons on shell. And then in the factorization formula, the convolution variable X is from X Bjorken to 1. And we know which X variable we are probing. And especially at the leading order, this hard coefficient just turns into a simple delta function, and X is exactly equal to X Bjorken. So the X dependence is not something we worry about in inclusive process or in the global fit of PDF, but it is a huge problem for GPDs. And therefore, you would wonder, is this something we can overcome? And to think about this, we come back to the kinematic picture we had before. This is, again, the 2 to 3 process, and we picture this as happening in 2 stages mediated by this A star. And where do we have handles for the X dependence? It must come from the hard interactions probing it. So the hard interaction is described by 3 kinematic variables. First, it's given by its center of mass energy, which is S hat. And S hat is given by the total momentum fraction from this A star. And we know that is given by Psi. So this is not with X, this is Psi. And the second variable is the theta. And the third variable is the phi. And phi, we have also seen, is controlled by the spin states of A star. So it's not related to X. Only the dependence of theta or equivalently, we convert theta to the transverse momentum of C or D is related to X. And to put that into a factorization formula, we write the overall amplitude as the sum over all possible A states, and each A state gives us a factorization of this. We say this is a GPD, which depends on X, and the hard coefficient that depends on X, and the hard coefficient also depends on the theta. And the phi dependence is factored out. So from this, we can see the different roles of theta and phi. We use the phi to distinguish different A states, but we use the theta dependence to probe the X dependence. And then let's see if the hard coefficient we have here, which depends on X and Q is a generic notation for either theta or QT. If these two dependence factors into separate factors, we never end up having extra controls over the X dependence because Q dependence factors out and the convolution of GPD reduces to something here like this. And we only have dependence on psi and t, which are the variables of the GPD itself. And this, again, gives us the scaling phenomenon. But it gives us the inverse problem, which is the shadow GPT problem, because only having this kind of integrals, the inversion of GPT is a singular problem because you can have infinite solutions by defining this shadow GPT that gives 0 to these integrals. And this shadow GPTs can never be distinguished from the real GPTs. This, by the way, this doesn't mean that in reality, there are more than one GPDs because GPT by their operator definition is unique. It's just that the inversion from experiments is singular. And that occurs if we only have processes of this type. But if we can have some processes such that the hard coefficients really depend on the X and Q in a non-factorizable way in this way, then there is an entanglement between the Q dependence and the X dependence in this convolution. And from that, we can get extra sensitivity to the X dependence. And that has to break the scaling at the leading order. And to see what I mean there, let's look at the simple examples of DVCS. So why do we have scaling in DVCS? The reason is when we make approximations to obtain the factorization, we project the incoming and outgoing quarks on shell being massless. And now we also have the external state, the real photon being on shell. And in that case, the internal propagator K, when we make the calculation, we take a square of K squared in that in this denominator. And that simply gives us something proportional to X minus cosine because K is the sum of two momenta. One is, so this laser pen doesn't work. So because now this X minus psi line is light-like and this Q prime is light-like, we know that their sum and then squared must be proportional to X minus psi. And therefore, all the dependence on external scale is factored out, and we are reduced to this kind of simple integrals for the GPD, and that gives us a scaling. And we can make comparisons between this and the DRS, and the same thing happens here, except that for DRS, we make a cut on this K propagator. That puts the K on shell, and that sets this. This originally sits in the denominator, but putting it on shell turns it into a delta function. So we have a f and x Bjorken. Sorry, there's a typo here. This psi should be x Bjorken. So now we would like to gain something extra, and the natural way to do that is to make the Q prime off shell. And off shell can be obtained by requiring the final state not to be a real photon, but be a pair of leptons. And that gives us a double deeply virtual compton scattering, or double DVCS. And that name arises from here. We have two virtual photons, one from the initial state, one into the final state. And here we have an extra scale given by the square of Q prime, which is a Q prime square. And then by taking a square of this same momentum, we'll get an extra term, Q prime here. And that breaks the scaling. And that gives us the extra Q prime dependence in the denominator. So that's how we can gain extra sensitivity to the X dependence. And that requires scaling violation. However, you can simply count the electromagnetic couplings here. And this is at amplitude level. You need to square this to get the cross section. And the rate turns out to be very low. Although people have been trying to study this, and the general consensus is the rate must be too low to be actually useful. So we would like to have a scaling breaking at the 2 to 3 level, and we need to find processes of this type. And currently we have found two processes. One process is given by the collision of a pion with a proton, and the final state is the two photons. And the other one is to cross the photon and the pion, to have the collision between a photon and proton, and in the final state we have a pion and a photon. And the first process with the pion beam can be studied at JPark or AMBER, and the second one with the photon beam can be studied at JLab Hao-D. And we can quickly go through these two processes. And for the two photon process, we can have a look at the hard scattering process here. We have a pair of partons from GPD, a pair of partons from the pion, and they collide to produce the two photons. And we require the two photons to carry large and balancing transverse momentum. And that require a hard gluon to connect these two parton lines. And it is this QT flow that entangles with the X flow to give us extra sensitivity to the X dependence. And it turns out that we have extra sensitivity in the two declap regions for X to the left of minus psi and to the right of psi. And we can work out the cross sections, and just by taking a look at this formula, you can notice that it's hugely complicated because we have so many terms that occur at the same time. And that is the key feature of the diffractive process or exclusive process, because everything happened at the same time. And we don't have as strong constraints from the polarization as we have in the inclusive process. And we can test the sensitivity to the X dependent by creating different shadow GPT models, adding them to a certain given model, and make comparisons for the QD dependence or the theta dependence. And this different solution, different models give us different distributions for theta or for QT. So from this QT dependence, we can distinguish the shadow GPDs from the real GPDs. And for the second process, it's very similar because it's just the kinematic crossing. And we similarly get extra sensitivity, but here the kinematic crossing turns the extra sensitivity to the ERBL region. So this complements the other one we have just seen. And this process can be studied at JLab Hao-D, the GlueX collaboration. And here we not only get a similar thing, we get something extra, because by putting the photon in the initial state, we have experimental control over its polarization. So this gives us extra polarization asymmetries as signified by these different azimuthal modulations. And this gives us more independent observable that we can use to distinguish the different GPDs. And from these different models, we get different distributions for unpolar cross-section and the other three polarization asymmetries. And we have also, we can select the neutral pion and charged pion in the final state. And so I still have something to show, but those are not very important. I don't have to show them. So I make a pause here in case anybody has any questions. Okay, so I can stop here and skip all these different this slide to connect to the global analysis of GPTs using the machine learning method. And this is the recent global fit result. And just to show you that people managed fitting all the available data and 10 to 15 minutes. Might be interesting. Okay. Okay, so maybe I can quickly go through this. So from the previous discussion, we've seen that it's difficult to extract the X dependence of GPTs. And there is a huge issue of shadow GPTs that makes the actual extraction of GPTs very biased because following the traditional method, we typically parameterize the GPT first and then fit to the experiments to determine the parameters. But once you make a parameterization, you suppress certain shadow GPT solutions, and that makes the result highly biased. So one way to avoid that is to take a neural network method. And the way, this is something I have been working on, and the way we do it is to model the GPT as a discretized grid in the 3 dimensions of the GPT variables, x, psi, and t. And from this kind of grid, we can get observables for the, get prediction for the measured observables and compare with data. And to be able to control this grid, we use a neural network and in the model of normalizing flow. I don't have time to go into the details of normalizing flow, but just think of it as certain neural network model that tunes each pixel independently. And from this normalizing flow, we generate some image of the GPTs. And then from that, we calculate the observables. We make comparison with the data. We get a loss function. And then this loss goes back to the normalizing flow to tune the parameters again. And from this, we minimize the loss and we get a GPT image. And an example is shown here. This is just a proof of principle study. We start with a certain model called the GK model. And GK stands for names of 2 people. And from this model, we can inject a noise to make this image very noisy. And the aim is to see whether the neural network will be able to recover the original image by taking the observables we put in. And the observable we start with is the integrals of DVCS that we have seen several times now. And it turns out that with GPT, with only the DVCS integrals, we are not able to recover the image of GPTs. We are only able to recover these 2 ranges, and one at x equals psi, one at x equals minus psi. And this is exactly as expected because we have a pole at x equals psi and minus psi in the hard integration coefficients. So for DVCS only, the sensitivity is only on the range. But then, so then if we also include some extra observables, something like the x moment integrals of GPTs, and this is something that can be obtained from other sources, like the form factor constraints, like the lattice QCD calculations, And it turns out that this is not sufficient. The resulting GPT still can have a large fluctuation with respect to the original GPT models shown by the black lines. And now if we also include the non-scaling process, the food production process that I just shown you, we can recover a large portion of the GPT image as shown here. And if we also include the other one, both the non-scaling processes, we managed recovering all the GPTs as shown here for 3 different illustrated psi values. The X curves for recovered GPTs almost match the original GPTs exactly. So that completes my story about neural network treatment. And now, before ending, I want to show you some recent progress from the global fitting group called GUMP. And this GUMP method is based on certain parameterizations. And although it's meant to be very general as possible, in reality, they have to truncate their expansion in a certain way, which following our previous discussion still inject certain bias one way or the other. But the GUMP group managed to fit in all the available data for DVCS and DVMP data, and also to the PDF and the form factors. Sorry, not form factor, X moments, and they managed to getting a decent fit. And from the result, we know that GPT encode the 3D images of the proton. So the result gives us this kind of pictures. Take this result with caution because the fitting of GPT is still far from being complete, but just confined within their result, we get the image for the up quark in this column and down quark in this column. And the color coding is shown here. Yellow means densely distributed, and this dark blue means no quarks or no other partons. And the horizontal axis refers to X, vertical axis is Y. And this is the transverse plane of the proton. And here, why are they not centered around the origin? It's because they are looking at the proton transversely polarized along the X direction. And with the transverse polarization for the proton, the parton image will be slightly distorted to one direction or the other in the Y direction. And you see that up quark tends to be on the positive Y and down quark tends to be on the negative Y. And that's one result. And this is for the gluons. And this axis for different X values, and the horizontal and vertical axis is for the X and Y. Oh, sorry, this is for the horizontal axis for the transverse radius B, and the vertical axis is for the density. And you can see that as X becomes smaller and smaller, the vertical values of this density becomes larger and larger, which means the radius of the gluon distribution becomes wider and wider. And this is for unpolarized proton. So let's summarize here. We have seen that the factorization can be extended from inclusive to exclusive processes. And this factorization introduces new correlation functions called distribution amplitude and generalized parton distribution functions. And I have also told you that the exclusive processes are far less well studied than the inclusive processes. So, and still a lot of efforts are put in this field, and you should expect a lot of further new development to be carried out in the following years. So this is not a settled story, but for the distribution themselves, the GPDs provide tomographic images, which is highly interesting. And for the phenomenology, we outlined the single diffractive hard exclusive processes to study the GPDs. And this provided unified pictures for all possible processes. And it entails a nice quantum interference patterns. And the key problem underlying the extraction is the inverse problem or the X dependence problem, which really requires some processes to give you enhanced X sensitivity. So, but with the fit people have done so far, things seems to look consistent, especially with the confirmation of scaling from experiments. But in terms of the full extraction of GPD, we are still not there yet. So in the following years, we should be looking for more processes and using more observables from more different experiments. And it's highly possible that this will require input from lattice QCD to fully constrain the GPDs. And that ends the lecture today. Thank you very much.
Thanks a lot. Any question?
Thank you. So using neural network to extract GPDs is kind of fitting without setting the function that you fit with. So neural network decides on itself, right? Is it like a correct understanding? So what are the disadvantages of this method? Because now it sounds that using neural networks to extract GPDs are superior to any other method.
So it looks so, but there are always some caveats using neural network because neural network itself injects some bias, and that's still out of the control in our current understanding, right?
But I thought, so when we use neural networks, it's like the least biased way to extract, because when we just feed, we manually kind of set the function that we fit with. So the analytical expression with free parameters, and we fit with this. When we use neural network, we just it decides on itself basically, magically, right? So it's kind of less biased way, right, compared to the others.
In principle, yes. That's why we are adopting the neural network way. But neural network also, you need to decide what kind of neural network model you use, right? And that's some neural network bias, right? And how many layers you use and what kind of loss function you use. And that's always something that currently cannot be fully settled. But in comparison with a parameterization form, you have more control. So although you may argue there's more bias, but there are pros and cons. Yes.
Thank you. Any other questions? Nope. So let's thank Zhite again for all the efforts, input, organizing these lectures, which are quite nice and very explanatory. So thank you very much for all
Thank
these
you.
lectures. Yeah.